Hello, everybody. Welcome to our live webinar, where we shall be looking for growth opportunities in the next generation of materials discovery. I am leading currently the Chemicals and Advanced Materials cluster in Tech Vision business unit of Frost & Sullivan, where we look for growth opportunities around various aspects of chemicals and materials like advanced coatings, surface technologies, high-tech materials, nanomaterials, and so forth. We have with us in this webinar Jabez Mendelssohn and Hina Juneja from Frost as internal panelists, and I would like to welcome Ali Najafi from ANSYS and Ethan Mirsky from Noble AI to our webinar. Hello, everybody. Welcome to the session. So if I would take a moment, we shall go Jabez, Hina, Ethan, and Ali. If you could please introduce yourselves.
Thanks, Abhishek. I'm Jabez Mendelssohn, research manager at Frost & Sullivan, where I lead research on the microelectronics, sensor technologies, and the automation space. I'm really excited to share insights on how AI and quantum computing are impacting the materials discovery, especially from the lens of hardware innovation, manufacturability, and real-world deployment.
Thank
Hina?
you, Jabez.
Yeah, thank you. Hi, everyone. I'm Hina Juneja, and I am an expert in the ICT domain, leading the ICT cluster as of now. And yeah, we generally track, advanced technologies like AI, IoT, quantum, and blockchain, and many more.
Thank you, Hina. Ethan, would you like to introduce yourself, please?
Sure. It's great to be here. I'm Ethan Mirsky, Chief Product and Strategy Officer for Noble AI. As we'll talk about later, we're a provider of practical AI-powered software that empowers chemical and energy companies to accelerate development of better performing, safer, and more sustainable chemicals, materials, and formulations. My background is in a variety of engineering and scientific products, including semiconductors, telecommunications, biomaterials, and AI software. And I'm excited for this conversation topic today.
Thank you, Ethan. Ali, could you please introduce yourself?
Hello, everyone. My name is Ali Najafi. I'm leading our application engineering team in the area of solid and structural mechanics, which is focusing on materials, structures, as well as manufacturing process simulation at ANSYS. ANSYS, as probably many people know, is a leader of simulation technology, primarily focusing on solving application problems. And in addition to that, I'm also holding a role of leader of our Center of Excellence related to integrated computational materials engineering at ANSYS. Thank you.
Thank you for the introduction, everybody. So if we can move to the next slide. So this, just to set the premise straight, these are the few questions that we shall try to answer and address during our webinar. So we have broken down into 4 parts. Let's start with the first one. What are the emerging trends in the chemicals and materials ecosystem that are driving the need for AI and quantum computing for accelerated material discovery? Next, we shall see how are AI and other quantum technologies aiming to transform various discovery workflows in material science today. Then we shall move to see what are the biggest barriers to the adoption of such emerging technologies in materials discovery. And finally, we shall try to evaluate what are the growth opportunities that could exist for companies embracing such emerging technologies like AI and quantum computing for their discovery models. Starting with the first topic. So we tried to analyze from Frost's perspective and saw that there are a few shifts, and they are driving, shaping the computation innovation and driving the discovery workflows. They are like the growing demand for eco-friendly, recyclable materials and is driving the adoption of AI for faster alternative discoveries. This is quite important to manage the sustainability profiles. Next, we are also seeing multifunctional materials that are requiring deep simulations beyond traditional methods and are getting accelerated by such AI and QC integration. Next, we also see that compressed lifecycle push the need for rapid validation of various materials using AI-powered discovery platforms. We are also seeing that AI-driven labs and digital twins can further enable data-rich, closed-loop discovery ecosystem. So to start with the discussion, I would want to ask Hina, how are you seeing the AI-ready labs and digital workflows change how materials data is captured and used in R&D pipelines?
Yeah, thank you, Abhishek. So, yes, I would like to, start, how AI and quantum computing, basically are revolutionizing the way we are discovering, designing, and basically deploying new material. So, material discovery has traditionally been slow and expensive and, always have been following the trial and error method. And this can take over decades and, billions of dollars to form just a new material or, move from concept to commercialization. Now, if we talk about, this is a bottleneck, and it just limits the
Mhm.
innovation, right? And the urgency
Yeah.
today, the way we are, pacing in today's technological era, to develop sustainable materials or maybe let's say high performance batteries or even efficient catalyst. The demand is growing day by day, and that is why the trend of adoption of these technologies is ramping up, right? So
Right.
starting with artificial intelligence, right? So
Mhm.
AI is basically transforming material science by, you can say, enabling data driven discovery. And here, models like machine learning models can help you analyze vast data sets of chemical and physical properties to predict the behavior of new compounds. Wherein, we use generative models that can actually help you design molecules with, let's say,
Mhm.
specific or desired characteristics. In fact, generative AI has actually helped, discover over 2 million new catalyst structures, sorry, crystal
Uh-huh.
structures, and
Uh-huh.
out of which 17% are stable materials. And these materials can actually help you revolutionize batteries and superconductors. So this is
That's
how
awesome.
this is how this technology is, and how strong it is, and it can actually
Mhm.
revamp the way we are using materials across industries today. In fact, Nvidia has
Mhm.
also come up with again a generative adversarial network, which is a model for
Uh-huh.
generating, and it has it will help you know with the help of basically this technology, it can design novel materials and by learning from existing databases.
Great.
Similarly, yeah, it is actually AI is creating a lot of changes and transformations across industries, and chemicals and materials is one of them. So now I would like to take the conversation forward to quantum computing as well. So quantum
Mhm.
computing also offers a fundamentally new way to simulate molecular and atomic interactions, and that too at a very extraordinary rate. Like classical computers really struggle, with a lot of complexity, absorbing a lot of complexity, I would say. But quantum can actually, take the simulations to the next level. And if we use AI and quantum together, the convergence is basically can help you, create very powerful hybrid models. While AI can optimize quantum algorithms, quantum computers can also enhance AI models through quantum machine learning. Now, this synergy is accelerating material discovery by enabling, again, faster simulations, better predictions, and more efficient experimentation. So yeah, this is how the trends in AI and quantum are you know changing the chemical landscape.
Well, this is quite interesting. Proceeding forward, Shabazz, I would want to know from the instrumentation side, how are these new sensing capabilities supporting faster or more precise material characterization? If you could explain it to us.
Yeah, yeah, sure. So by and large, across the semiconductor industry, especially in the microelectronics and the sensor innovations, we are
Mhm.
witnessing these irreversible shifts, driving the integration of AI and quantum computing into materials discovery. Let me just highlight three of them maybe. So one is being the eco materials mandate, with regulatory pressures on rare earth as risk factors. Sensors and chip makers are under pressure to pivot. So this accelerates the use of AI to identify alternative materials for, say, MEMS, power devices, and even packaging. uh, the other, the trend which you have mentioned here is the complex simulation requirements. In the electronic space, as we push into SiC, GaN, and 2D materials, high precision modeling is no longer a luxury; it's an essential requirement. So traditional simulation techniques would not be able to handle the quantum, the mechanical complexity required to understand these materials. So this is where we feel quantum computing, although still early but evolving, would become a critical factor for predicting material performances under thermal, electrical, and even mechanical stress. And the other one which I wanted to highlight from a semiconductor and a hardware perspective is the product lifeline compression. So in a
Mhm.
market where the time from concept to device shrinkage is radically collapsing, AI accelerates discovery and validation cycles. So we see this in logic nodes, sensors for automotive like lidar, and even in flexible electronics. So materials need to be screened, simulated, and qualified faster than ever, and we feel only AI would make that viable. So in short, from a semiconductor and a hardware perspective, we are looking at a convergence of sustainability, complexity, and speed, and that is precisely where AI and quantum tools can deliver value.
That's very interesting to know. Uh, Next, I would want to ask Ali. Ali, you have been extensively working on around the ecospace space of simulations and modeling tools with some enabling technologies. Could you please give us your opinions on how are some of the key trends shaping the computational workflows?
Yes, absolutely. So, I mean, starting, I mean, a little bit about trends because we want to see where industry is headed, where the problems and challenges are, and how we can align ourselves with those needs. And obviously, quantum computing and AI specifically, they are two key enablers with very high potential to address some of the challenges that our industries are facing. And obviously, there are, as all the panelists mentioned, drive towards sustainability and energy storage as a whole. Obviously, there are demands on making our supply chain more resilient and being able to accelerate selection and vetting of different supply chains, and also obviously accelerate the top time to market. Looking at different, let's say, verticals, industry verticals. I mean, you see there is demand for innovation. Obviously, energy is on the top with a lot of demands on sustainability and also alternative energy, followed by high tech, as Jay was mentioned. I mean, miniaturization and having additional, let's say, requirements on multifunctional material, 3D IC, where people want to kind of build the whole chip, kind of similar to 3D printing, as well as a lot of demands on automotive in general for safety and reliability, as well as performance. I mean, all of these, and defense and healthcare, all of these are big drivers that
Mhm.
we need to take another look at our material system to make them a better fit for these different purposes. And for that, I mean, obviously, as Hina mentioned, the development of material and alloys are a pretty long process, sometimes between 5 to 20 years. And we definitely see that computational modeling as a whole, with different methodologies such as AI, including AI and quantum computing, are going to be a huge enabler to accelerate this process.
Understood.
Yep.
So if we can move to the next slide, please. So could you please explain us, Ali, what ANSYS means when they say they are aiming to redefine simulation?
Absolutely. So at ANSYS, actually, we have three buckets of product or three layers of products. Products that are focused on simulating different physics using different computational technologies, from, let's say, structural mechanics to optics to fluid dynamics and electronics and electromagnetics, right? So those are those are the methodologies that engineering methodologies that require a lot of computing, and we want to kind of have a 3D idea of what is really happening in these different devices or different components that have these different properties, right? So that's been actually our traditional focus of simulation technology. But recently, in the past decade or so, we have been also investing on platforms and ecosystem to bring all of our capabilities in cloud, and hopefully at some point have them to be working natively on cloud and enable collaboration. And also on the other side, looking at platform, trying to kind of expose all of the capabilities that exist in our solver, as well as developing a lot of generative AI capabilities and large language model capabilities to be able to autonomously help with engineers and first to automate the workflow and also extract additional insight and knowledge and accelerate that using AI and our platform. And that where basically I believe quantum computing is going to be helpful, because in order for you to make a great decision in engineering, it's better to look into probabilistic method, and I believe quantum computing is going to be a huge enabler. I mean, not yet, but it is when it becomes mature, this is going to be a big enabler. So that's basically how we are approaching different problems. And obviously, when you look at material system, the high level requirements has to be translated into physics, and from the physics, they go deeper into what is needed in terms of properties. So if we build these, let's say, digital workflow from requirements to physics and ultimately to material and computational chemistry, we are able to develop a digital thread that can be adjusted based on different needs, and it can optimize and hopefully at some point give you a recipe of proper material that meets your requirement from manufacturing perspective, from sustainability perspective, and all the other requirements that the customers have.
That's very interesting to know. Thank you, Ali. Ethan, I would want to bring you in. Can we have the next slide, please? Ethan, what do you say are the key trends that are shaping the chemicals and materials landscape, and how you are trying to approach or leverage it? If you could please tell us.
Sure, happy to do that. This slide just to introduce who we are. As I mentioned at the beginning, we're a provider of practical AI software for chemical and energy companies, partnered with several leading companies in chemistry, energy, and IT, including Microsoft as a major partner. As I'm sure everyone's aware, I mean, the large LLM style AI models out there. And everyone's also aware that these face significant challenges when it comes to chemistry and materials, and we'll talk a little bit about that later. And so Noble AI exists to address that and use AI, because not everything is an LLM. Not all AI is one thing, and so we're all about using the right technology for the right problem. And again, we'll talk a little bit about that later. But specifically with regard to the trends, some of the things you put up earlier, we definitely see regarding regulation and safety. I mean, there's more and more scrutiny these days on chemicals and materials, PFAS being a great example that everyone knows about. Things that have been in use for a long time are now being seen as hazardous and need replacement. And so there's a major push to fix all of this. And it's important that these alternatives work from both a performance and a cost perspective and a manufacturing perspective. So all those pieces have to fit together. And it's that complexity, I think, that really drives a lot of the need for AI. That materials are more than just multifunctional. They have multiple aspects. There's multiple different kinds of physics. Even in a simple chemical diffuser, you've got diffusion, you've got evaporation, you've got chemical reactions, you've got all kinds of things going on. And to model all of that along with from the micro scale to the macro scale to the physical properties, plus you have business costs, you have some material availability, you have regulation. And to put all of that into one piece is really complicated, and that's exactly what AI is really good at, is taking these big complex pictures and synthesizing it. And so we definitely see that as a major driver.
Understood.
Sorry. And then, yeah, we completely agree on the compressed life cycle needs. And again, this is whether that's in consumer products where consumers want new designs, new products every quarter, every season, or even if it's just the pressure from investors to do more with less. AI, we know AI improves productivity on the business side, but how do we make it? How can we make it work for the chemists, the product developers, the people who are really actually making the real things in the real world? And what's exciting now is that it's possible to do that, and it means that companies that don't use AI are at risk of falling behind. So that's another major driver here. I'll stop there for the moment.
Understood. Really, that's a very interesting thing you were saying. Of course, it's a very interesting thing to hear. Like, that's what we are trying to figure out. The companies who are investing in AI right now, will they be having the leverage in future, and how it's gonna shape? So we shall be now moving to the next topic, and we shall be trying to understand how is the landscape developing for chemicals and materials discovery by leveraging AI and quantum technologies. So these are some 5 different points that we could identify. They are like machine learning models for predicting properties, performance, and formulation behavior, and these can be applied to designing catalysts and polymers with tailored characteristics. We also see that quantum algorithms for simulating complex molecular and electronic applications are also developing, and they would find application for discovering energy materials with better durability, efficiency, and charge performance. Concurrently, we see that digital twins and automated smart labs are developing for real-time iterative experimentation, and these will find applications for predicting the degradation of coatings and composites under real-world conditions. Like that, we see knowledge graphs to unify the structures and unstructured materials data, and will be used for formulating the next-gen adhesives and other kind of functional materials with fewer trial and error cycles. And finally, we see cloud-native platforms as a key enabler for scalable, collaborative, remote R&D environments, and they shall be enhancing the structure property predictions for nanomaterials and other hybrid systems. So can we move to the next slide, please? So before we go there, I would want to ask Jabez, you are seeing from the sensor side. How can you tell us these automated labs and digital twins are improving experimentation cycles in practice?
Yeah, sure. So as mentioned earlier by our panelists, this is an exciting space where these changes are not theoretical. They are happening in production environments today. And just to give you some, live use cases where, AI, maybe an example of AI in fab operations. So companies like TSMC and Intel, for example, are using AI for, process optimization in EUV lithography, leveraging predictive analytics to identify drift and tool anomalies. Similarly, digital twins are being used in MEMS and sensor production. As you may know, Siemens and other advanced manufacturers are already enabling full stack digital twins to simulate a MEMS gyroscope behavior and even wafer wrappage under various process conditions. So these, are reducing trial runs and even costly failures. This could also mean the creation of adaptive testing environments where emerging AI-powered R&D environments, simulations are constantly refined by real-world data. So this could allow the manufacturers to build adaptive material pipelines where the output of the test labs immediately loop back to the discovery algorithms. So this could in turn reduce redundancy and also enhance reliability.
Understood. That's really interesting to know. Hina, could you tell us what role do these knowledge graphs or cloud native platforms play in scaling material informatics across organizations?
Yeah, sure. So, you know, what I'll do is I'll probably, pick up some cases wherein, I'll explain how, maybe AI and quantum simulations are helping, transform the materials area. So, if we talk about, let's say, battery materials, right? So AI and quantum simulations, help you to identify new solid state electrolytes and you can say, cathode materials. Now companies like Toyota and QuantumScape, these they are using AI to discover solid state electrolytes that are safer and you can say more efficient. In fact, companies like IBM, Google, Quantum, sorry, and startup like Zapata AI, they are basically using hybrid quantum classical models to create complex materials like high temperature superconductors. So, these kind of advancements are happening in this space. In fact, there are advancements related to carbon capture as well. So if you talk about knowledge graphs and, or maybe, generative AI, they can help you, design porous materials for efficient CO2 absorption. Like there is a company called in-silico medicine. So they are leveraging this technology to define porous materials for carbon capture, and they are aiming to reduce CO2 and CO2 capture by over 50%. So uh, these are some of the examples. In fact, researchers, have been using quantum computer to, simulate a superconducting material behavior, wherein, cutting down computation time for months to days, and that's considerable, right? So this can actually revamp the the innovation cycles, the work cycles of the entire, material production. And this is particularly valuable for understanding reaction mechanisms like electronic structures and material properties at quantum level. So there's one company called QCware, and it basically offers a hardware agnostic software solution. And this company basically plans to expand its platform in different, industry areas, and particularly specifically for material science, logistics, and even in material learning applications. So yeah, these are some of the notable changes and notable innovations that I've come across, and these can actually enable different sorts of applications in the industry.
Thank you, Hina. It's very interesting, like you said, that we are seeing a steady interest coming from both the incumbent as well as the startups or spin-off sites. Yeah. So next, we can ask Ethan. Ethan, could you just explain what you were doing and how you are trying to disrupt the landscape? Can we go to the next slide, please?
Sure. Yeah, so just quickly on in terms of the transforming workflows, one of the things Jabez and Hina, the way they talk about it, I really see there's sort of two different angles here that these technologies can apply. First is what is being worked on. So whether that's new materials, new formulations, complete systems, the ability of AI to encompass that whole spectrum really enables new things that you never would have imagined you could use computational tools to work with. But even more significantly is how that AI is changing how the work gets done. And so that's involving the workflows, being able to accelerate the decision making, being able to make more confident decisions, running these thousands of virtual experiments in minutes and summarizing the results, those kinds of things. And so we really sort of play in both of those areas. And so what you see here, I mean, starting with sort of the what, it really is based on the kind of models. And as I talked about earlier, chemicals and materials, it's a combination of all these different types of science, different scales, and one size doesn't really fit all in terms of the approach. An LLM is not good at some things. Certain kinds of ML models are good at others. We combine all those things, apply the right technology to the right problem, build it holistically with the most relevant and available information. And each model is custom built and optimized for its use case. And this allows you to solve some of the key problems in chemicals and materials, which is you don't, and we'll talk about this a little later, that we don't have an internet's worth of data in many cases for a model to be built on a specific problem. Privacy, security, IP protection are key elements to this field. And this is something that more traditional AI doesn't do so well, but it is possible to engineer these systems to actually do that. And that's what we really focus on here. So building these models that can cover the needs of the real world chemist, material scientist, engineer, product developer. And we combine that, please, next slide, please, with a platform. As Ali mentioned, platforms are key because that's what enables people to work with these models. Just having the models alone aren't enough. And you need to be able to have that usable, not just by data scientists or AI experts, but lab scientists, product managers, risk managers, everyone in the field who's involved in making a product should be able to use these tools. And it requires a platform that enables predictions, explainable insights. It has to be understandable, something that a scientist can look at and understand what's really going on in the system that they're working with. It can generate these designs, solve the problems across these scales. And of course, it has to be something that is IT can support. I mean, it's easily scalable across an organization, providing all the necessary security and privacy. And so, yeah, we're cloud native in AWS, Azure, cloud. You pick your cloud of choice, and it covers the entire organization. And so, just to, I don't have obviously time to show you everything. Go to the next slide, just to give you a bit of a highlight of the kinds of things that you can do. So in the upper left here, we're showing an output of an inverse design. So this is an example where you have those orange dots represent experiments that you've done, and you have this multifaceted problem. You're trying to optimize multiple variables. An AI can come in and in just a few minutes generate these thousands of blue dots of experiments that you didn't have to do, but that push the limit of what you're capable of, the improving and optimizing the design over previous formulations. And then obviously you can click into each of these and see what they are, explore them, understand what makes them better. And then on the upper right is an example of some of the custom charting, which really allows you to quickly see and understand what's going on. So again, multi-dimensional. So you've got heat maps. You can explore many different variables at once and really, again, get that clear sense of what's going on. And then because we're talking largely about molecular design, we also, focusing on that sort of interactive design where you want to see the molecule that you're working with and figure out, well, what happens if we change this? What happens if we change this other thing? How do we make it better? And explore that design space and see the properties in real time with the predictions and results that you're looking for. So again, it's really about taking, I think Hina mentioned the months to days. We talk about months to minutes. And that's really the power of these tools.
So true, Ethan. Next slide, please. Ali, I would want to bring you in. And if you could take us through the ICME portfolio, make us understand how is ANSYS taking this opportunity and trying to solve these accelerated R&Ds.
Yeah, actually, before I cover my slides, I wanted to echo what Ethan mentioned about the variety of different methodology that exists to address different challenges in material and methodologies that help with discovery. And I mean, so different material systems, alloys, multifunctional materials, traditional materials, polymers, rubbers, these different types of materials, adhesives, they have different chemical or molecular structures. And as a result, you have to solve these different problems with different sets of, let's say, computational models. And when you look at basically our entire universe of, let's say, different elements that exist in the world and everything, right? So there is a huge number of, let's say, methodologies that are developed specifically for a specific type of material system. And that's actually makes this, let's say, design space extremely huge and difficult to manage. And this is actually where AI can help to kind of organize these types of knowledge and help people to kind of pick the right algorithm, pick the right methodology for their best use, or use these types of ensemble model that Ethan mentioned to kind of let the code to decide based on existing information and requirement on what is needed to be incorporated or captured, right? And then that's one layer. The other layer is the microstructure. I mean, morphology. Hina mentioned about amorphous materials and ability to adjust material behavior and material property to, let's say, bones, because bones are also amorphous. And that also different layers. And I mean, basically designing the microstructure, which is in another level of, let's say, scale, length scale, is extremely important. And also this is where you can also tailor your and leverage your manufacturing process parameters to design your morphology or your microstructure as a whole, right? And then from a bigger picture perspective, how this material gets represented in, let's say, a bigger digital twin that can help you to do predictive maintenance and so on and so forth. So these are, depending on where you are and what type of material system you're looking for or what type of leverage you have, these methodologies are different. But as a whole, when you look at material space, these are some of the major and most important points that you have to keep in mind that are shown in these dots. Basically, we definitely need to use our database and manage our database, make it more traceable. I mean, the first starting point is to look at what we have, and this is where material selection is going to be extremely helpful. Using traditional approach of selecting materials such as optimization and more modern approach like machine learning or even AI in that space. And then once the material is conceptualized or conceptual design of material is done, I mean, definitely in many industries, we have to definitely do testing. And usually those testing are through some standard recommendation, but the most important thing is as materials requirements and and functionalities are becoming different, we have to develop more advanced testing program for those materials. So we have to keep that in mind. And then in order to use these types of information in our modeling approach, we have to perform calibration to make those information, experimental information, useful for computational modeling. And obviously, we have to look at performance as well as manufacturing. And when you put all of these things together, these are some of the capabilities that we have in ANSYS portfolio that helps kind of going deeper into these different topics. Some of these tools and features are, many of them are native in ANSYS, and we also offer with our partners some of the solutions, let's say in polymer space, in metallic alloy space, in manufacturing, process simulation space. And the key here is that in order for you to have a innovative platform that runs fast, you have to kind of bring all of these things together. And if you go to the next, if you click one more time, you have to connect these different, let's say, aspects together. And this is where, again, AI and high performance computing is going to be extremely useful. Even today, with all of the progress that has been made on GPU technology, we see a huge jump. And I mean, that's both on the hardware side and also on the software side, by optimizing and making our software more basically adjusted to the capabilities that these new computing platforms are providing. I mean, obviously, quantum computing is going to make this even more compelling, because you are building your model. Basically, once you generate or once you train your model and you leverage your data, and then it is a deployment aspect. But on the scalability, definitely these computing technologies are going to be extremely useful. So that's one aspect of, let's say, how AI and ML, probably ML more specifically, and computing are all can come together to develop, to kind of build this ecosystem or workflow for different material system. And you can be selecting some or all of these different, let's say, tools or verticals to chain them together and accomplish a task. That task could be an inverse problem, similar to what Nathan mentioned, looking at requirement and going back to recipe of material, for example, or adjusting material, inserting additional, let's say, chemical or composition or additive to your existing material to make it more fit to your purpose. Or it could be just analyzing and getting additional insight about what is happening as you basically see this, let's say, these material being used in a component, in an assembly, in a system in the field. That's one aspect. The other aspect, as I mentioned, I mean, there is a huge, and if you go to the next slide, there is huge amount of knowledge that is being out there related to material science. And part of, I think, part of this revolution of AI could be bringing these knowledge and organizing these knowledge and make it available to many people. I mean, different material system requires years of experience and expertise. So we believe LLM can help doing that. And actually, we started kind of bringing and putting together the knowledge that exists inside ANSYS as a chatbot and advisor to begin with. But and hopefully in future we can merge and we can append additional, let's say, vertical knowledge information into this ecosystem, so that we can advise people on what methodology to use, and even take it to another level and make it entirely autonomous. So that's where we are headed when we're talking about a combination of large language model. And this is our first experience, the first product that we have released almost about 2 years ago, which has been evolving, which is built based on multi-physics knowledge that has been collected in the past 50 years of ANSYS.
That's quite interesting to know. Thank you, Ali, for letting us know that. Moving to the next topic, we are going to look at the barriers to adoption for such emerging technologies. Yeah, there could be quite a few, but some of the key or the top four that we identified were like lack of high quality structured data, limited interoperability across various instruments, platforms, and other ecosystems, high costs associated with implementing such kind of enabling technologies, and uncertainty around the ROIs and long-term business impact. So the adopter perception, we can say there. So Ethan, I would want to quickly bring you in, and could you please give us your peace of mind on what do you see as the barrier to adoption of such technologies?
Sure, happy to. So generally agree with all of this, but let me add a little bit of color here. Regarding the lack of data, and as I mentioned, this is a big problem for the traditional type of AIs, because while there certainly is a lot of data, most of it is sort of generalized, not specific to a particular problem, really not the kind of data that you need to solve the kinds of problems that you really want in the real world. I mean, if you weren't doing something on the cutting edge, trying to advance, you're not really making any progress anyway. So the key thing is that what we find is, again, by incorporating a lot of the science into the models, by really designing the model specifically to solve these particular problems and having them be able to be built quickly and automatically on platform, means that you get started with a lot less. And we often find companies that are reluctant to start an AI project because they feel like they need to go through a huge exercise of organizing all their data and capturing it into some kind of system first, which of course is a huge endeavor and probably will never actually finish. And just realistically, these kinds of projects really just drag on for a long time, at which point you're falling behind. You're missing the opportunity when in reality, if you have a problem, bring the AI in, start working with it immediately with what you can, and you can make a huge amount of progress even with minimal data. Regarding the cost of the infrastructure and talent, and certainly this is again where the platform approach comes in, where you don't have to have AI experts on every single problem, every single solution you have. That's another concern people have, is like, hey, I don't have the data scientists, I don't have all the AI experts. Well, you don't need to these days. The tools are at a point where you can utilize experts who've built their expertise into tools, and get that value right away. And then one last point, uncertainty, I think, is probably the biggest barrier. This concern that, hey, I mean, people in the chemical material space, I mean, they're not AI experts, and AI is changing really fast. It's really complicated. It's hard to keep on top of. And so there's an obvious reluctance, like, hey, I don't know which way to go. And having that confidence, and so adopting new technologies is concerning. But again, this is where coming to the experts and relying on those who have built these platforms for these purposes allows you to sort of get started easily with very low risk. And that's really what you should be looking for, is not trying to be an expert, because the tools will always be changing, but look to those who will support, take advantage of all those changes and allow you to move forward. So that's how we see it.
Thank you, Ethan. To add to it, Ali, do you have anything?
Yeah, I just wanted to add a few other points. I mean, in terms of 100% agree with what Ethan and you brought up. In addition to that, I think there are some IP concerns when people want to use their own data and how the data has been handled. Obviously, if it is natively done in the organization, that increases the cost. And this is related to talents and having a kind of a different, let's say, talent acquisition for the companies to be able to do that if they want to put it out there if they want to expose it to third party. There's going to be always the risk of losing the information and IP. I believe this has been always a challenge, and I think it's going to remain a challenge, specifically for AI. As a whole, in material discovery space, I believe if you want to look at this new paradigm of work where we are collectively trying to work together to design a material system based on a specific performance, because of the fact that it involves with a lot of different disciplines and different expertise and requires a lot of collaboration. I believe many of our organizations are not properly structured to address those types of needs. And that's also goes back to amount of investment that people have to make and uncertainty associated with those investments. But I believe there has to be a little bit of a mindset shift in order to enable these types of, let's say, agile type of looking at material system and material design. Traditionally, people have been looking at material selection rather than material design and material discovery or insertion and so on and so forth. And that requires an organizational change and cultural change of collaboration as well. And also, I mean, basically I mean, there is definitely uncertainty with all of those things, validity of the information, because I mean, when it comes to material is the foundation of any type of design that we do. If you want to, that's basically you first you have to make a choice on your material before you design your product. And that's a huge commitment. As a result, changing that and revising that material system later in the design cycle, it's going to be extremely cost uh, costly. And because of that, I mean, I totally understand there is a lot of uncertainty because you're kind of handing that uncertainty to, let's say, AI agents or the things that you might not have proper experience or legacy to work on. So these are some of the things that I just wanted to bring up in addition to what other panelists mentioned.
Thank you, Ali. Should we go to the next slide, please? We shall proceed to the last chapter, and we shall be looking at what could be the growth opportunities here. So we could identify a few. They are some of the topics: accelerating time to market by rapidly screening candidates using various kind of simulations, uh, enhancing molecular design by leveraging quantum computing for high accuracy property predictions, improving R&D efficiency by integrating such kind of instrumentation and AI workflows, discovering new materials via quantum-enabled explorations, and fostering cross-functional innovations by uniting artificial intelligence, quantum computing, and domain expertise in material science. That being evaluated, I would want to quickly ask Jabez. Jabez, what are the most exciting opportunities you see for smart instrumentation to accelerate discovery in industrial R&D?
So for companies in this space, there are several high impact growth opportunities that matter. The key ones could be the quantum supported material insights. So companies like Intel, IBM, and even academic groups are experimenting with the quantum simulations of dopant behavior, atomic interfaces, and even energy band structures. So this could offer as a roadmap for 2NM and beyond. The next opportunity could be a AI robotics smart lab, where we are seeing pilot examples, including MIT and Google X, of AI systems autonomously selecting and testing materials. That model could easily be adapted for sensors, MEMS, and even power packaging lines. And the other opportunities could be cross-domain collaboration models, cycle time compression, to name a few.
Understood. Thank you, Jabez. Hina, I would want to quickly ask you, how do you see quantum computing as an enhancement or augmentation to further the AI-driven material discovery in the near future? If you could tell us.
Yeah, yeah, sure. So see, quantum is definitely, going to speed up the innovation, as our panelists have also mentioned. So, we will be seeing, some self-driven labs, that will come up. So these labs will have, fully autonomous material discovery pipelines, and these will be AI enabled, and it can actually accelerate the experimentation of new materials. And of course, as Ali also said earlier, bringing knowledge to one ecosystem. So, we will be in need of open source databases and models that can foster further collaboration amongst companies. And some AI and quantum tools, open source AI and quantum tools that I've come across are TensorFlow Quantum and Qiskit, which can be, the starting point as well. Another thing that I feel, will be a growth opportunity, will be, programmable matter can be easily discovered. And these are basically, AI design materials that can adapt, in real time. So these are more like those shape shifting structures. So yeah, that's from my end.
Thank you. Ali, I would want to bring you in. Do you have any perspectives or industry uh, insights towards what could be the great growth opportunities for enabling such kind of technologies for material R&D?
Yeah, absolutely. I believe actually going back and when we talked about the challenges, one of the challenges associated
Mhm.
with ROI, uh, we believe quantum computing is a huge enabler to make this process extremely fast. I mean, some of these computational modeling in molecular dynamics models are taking weeks to solve, and with a very small, let's say, representative volume element and so forth. So it makes it extremely difficult to really wait and rely on pure computation to address that. And this is one of the best fit for quantum computing. Theoretically, we are not there yet to see that, but if that happens, that will scales this by many orders of magnitude and make that process faster. And as a result, I believe the initial investment is going to be higher. As a result, the return of this investment is going to be less uncertain. So that's definitely one aspect. In general, I believe we need to see additional development at the software layers of quantum computing so that and also people have to, I mean, as a growth opportunity probably for software vendors, is that we have to also make our software and algorithms quantum ready. And those are big enablers that help with basically addressing some of the challenges that we discussed in the previous conversation.
Thank you. This explains a lot. Ethan, would you like to share some of your perspectives on what could be the most possible growth opportunities leveraging AI for accelerated materials discovery?
Sure. I mean, I think some of the stuff we see companies today already taking advantage of, and there's just so much opportunity to improve on. We've covered a lot of this, whether it's creating new materials or addressing the quickly deploying new formulations of existing materials to address the sustainability or regulatory impacts. Um, and then in general, just improving efficiency and decision making in R&D and operations. So getting away from needing to do the lab experiments or doing thousands of experiments in silico before you decide which are the ones actually worth doing. So it's really about reducing that risk. And it really does. I mean, it's not handing things over to the AI. It's keeping the human in the loop and having the AI be that partner to really help the human be most efficient and most effective. And then I think the real the next stage that's really coming is some of these knowledge graphs and other things to really help understand, well, what do you do like at the earlier stage? So not just sort of where you're trying to optimize material, but being able to say, hey, I'm starting from scratch. I want to know what should I do next? Having that AI be that thought partner basically to help you along, be in that field. I think that's a huge opportunity for the field.
Thank you. So yeah, I think we had a good discussion on the topic. So I would want to thank every one of you for sharing your insights. We just to sum it up, we identified some of the key trends that are shaping the new material discovery landscape. We tried to see how AI and quantum technologies, along with some other enabling technologies like cloud-based platforms and digital workflows, along with digital twins, can accelerate the discovery process. We also evaluated what could be the barriers to adoption and looked forward toward the growth opportunities. Thank you, all dear panelists.